Welcome back to Physics Classroom. In this lecture, we will discuss solution of ordinary differential equations using modified Euler and Runge Kutta methods. And also, we will discuss harmonic oscillator and particle in a box as examples with its Python codes. Here, we find the solution of ordinary differential equations. For example, dy by dx equal to f of xy be the differential equation with the initial conditions y of x naught is equal to y naught. Then we have to find y of x. So this is the solution. This y is the solution. In Euler method, we found that yn plus 1 is equal to, that is y of xn plus 1, which is equal to yn plus h into f of xn yn, where we assumed that this f of xy, the function f of xy in the interval xn plus 1 was assumed as f of xn yn. That is a constant in the interval, this xn plus 1 interval. Now we will see the modified Euler method. Here, instead of approximating the function f of xy as f of x0 y0 in the interval x0 to x1, in modified Euler method, we approximate this f of xy using the trapezoidal rule. That is, f of xy is equal to 1 by 2 into f of x naught y naught plus f of x1 by 1 in the interval x0 x1. That is, y1 equal to y of x0 plus h equal to y0 plus integral f of xy dx. So this f of xy is approximated as this one. So this is taken outside and the integral is integral dx, which is equal to x1 minus x naught, that is h. Then this f of xy is replaced by this one. So this becomes y1 equal to y0 plus it's by 2 into f of x naught y naught plus f of x1 y1. But unfortunately, this is like an iterative, since this y1 is not known initially. So this y1 is obtained using the ordinary Euler method initially. Initially, this y1 is obtained using ordinary Euler method and is written like this: y1 is equal to y1 of 0. That is, y1 of 0 is equal to y0 plus h into f of x naught y naught, as we have seen in ordinary Euler method. Now using this iterative method, iterative modified Euler method, this y1 can be written like this: y1 is equal to this one, where this y1, this obtained y1 is replaced here, so that this can be, this iterative equation can be like this: y1 of n plus 1, that is n plus 1 the approximated y1 is equal to y0 plus it's by 2 into f of x naught y naught plus f of x1 y1 of n, where y1 of n will be the previous calculated y1, where the initial y1 will be this ordinary Euler method y1. Now we will see an example for the Euler method, the ideal harmonic oscillator. Here we use the simple ordinary Euler method For the harmonic oscillator, we know the equation, the second order differential equation, d square x by dt square plus omega 0 square x equal to 0, or d square x by dt square equal to minus omega 0 square x. Analytically, we have the solution. We know the solution, that is x equal to a sine omega 0 t plus phi, where a is the amplitude. And the velocity will be v is equal to dx by dt is equal to the differential of this one, that is a omega 0 cos omega 0 t plus phi. In numerical methods, we integrate this second order differential equation twice. Integrating once, we get the velocity. Integrating this d square x by dt square once, we get dx by dt, that is velocity. Integrating twice using the Euler method, we get the displacement, that is dx by dt is integrating to get x. So x is the displacement. So this is the Python code for the ideal harmonic oscillator. Initially, the pylab is imported for plotting x, the displacement value, the velocity, the omega values are initially initiated with some initial values. T is initiated with 0. The dt or the step h is given as 0.01 second. Then empty lists are created for x dat, v dat, and time dat. Now a while loop is started. While t less than or equal to 15 means up to the time 15 seconds, this will proceed. X dat is append at x, v dat is appended as v, time is appended as t. Now this x is the new x value is found using the equation, using the Euler method equation, x equal to x plus, that is x0 plus h into v, that is x0 plus dt into dx by dt, that is the final solution. Then v is equal to v plus, that is v0 plus h into, that is dt into omega minus omega square x. So this is the first integration, this is the second integration. So using the first integration we get the velocity, then twice integrating we get the displacement or the solution. Now the time is incremented and this loop will work until the time is equal to 15. Now these results are printed. In figure 1 we plot time versus displacement. In figure 2 we plot time versus velocity. In figure 3 we plot displacement versus velocity, that is displacement versus, this is equivalent to displacement versus the momentum, that is the phase plot. So the result will, so this is the result of the program. Displacement versus time, we found that analytically the solution or the displacement is sinusoidal 1. So this is sinusoidal 1, and the velocity, the dx by dt, the differential of this displacement is again another sinusoidal function, and the velocity versus displacement, that is a phase space plot, is obtained as an ellipse as we expected. Now we will see what is Runge Kutta methods. So we found the modified Euler method as y1 is equal to y0 plus h by 2 into f of x naught y naught plus f of x1 y1. Now if we substitute y1 is equal to y0 plus h in the f of x naught y naught here in this position, it becomes y1 is equal to y0 plus h by 2 into this f of x naught y naught plus f of x1. This y1 is replaced by this one, that is y naught plus h into f of x naught y naught. Now this x1 is replaced by x0 plus h, and this equation is written in symbol format like this, that is y1 is equal to this y0 plus 1 by 2 into k1, that is h into f of x naught y naught is replaced by this k1, and h into f of x naught plus h plus this comma this 1 is replaced by k2. So this is the symbol form of this modified Euler method. So that this where this k1 is h into f of x naught y naught, and k2 is h into f of x naught plus h comma y0 plus h into f of x naught y naught, where this h into f of x naught y naught is again k1, so it is written like this. So this equation, this highlighted equation, is called Runge Kutta second order equation or second order formula, with k1 is equal to this one and k2 is equal to this one. Now we generalize the second order Runge Kutta formula. So we found the Runge Kutta second order formula is this one, y0 plus 1 by 2 into k1 plus k2. Now we generalize this one like this, y0 plus w1 into k1, that is some constant or some function into k1 plus some function into k2, where k1 is equal to h into f of x naught y naught and k2 is equal to h into f of x naught plus alpha 0 times h in general, comma, y0 plus beta 0 times k1 in general. So we can see that in the second order formula, this alpha 0 is equal to 1 and this beta 0 is equal to 1, and w1 is equal to w2 is equal to 1 by 2, so that we get this formula. So we extend this second order generalized formula, this formula, to the fourth order, that is we get y1 is equal to y0 plus w1 k1 plus w2 k2 plus w3 k3 plus w4 k4, where these coefficients w1, w2, w3, etc. will be different coefficients. We can select different types of coefficient to get different forms of equations, and this k1, k2, k3, k4 are these ones, where k1 is equal to h into f of x naught y naught, k2 is equal to h into f of x naught plus alpha 0 plus h, y0 plus beta 0 into k1, k3 is equal to h into f of x naught plus alpha 1h, y0 plus beta 1 k1 plus b1 k2, new 1 k2, and k4 is equal to h into f of x naught plus alpha 2h, comma, y0 plus beta 2 k1 plus new 2 k2 plus delta 1 k3. So choosing different alpha, beta, delta, nu, we get different equations. When we choose alpha 0 is equal to alpha 1 is equal to 1 by 2, beta 0 is equal to nu 1 is equal to 1 by 2, beta 1 is equal to beta 2 is equal to nu 2 is equal to 0, alpha 2 is equal to delta 1 is equal to 1, and this w1 W1 is equal to W4 is equal to 1 by 6 and W2 is equal to W3 is equal to 2 by 6. We get the fourth order Runge Kutta equation. That is y1 is equal to y0 plus 1 by 2 into k1 plus 2k2 plus 2k3 plus k4. So this is the fourth order Runge Kutta equation. So in this generalized formula, putting these coefficients, we get this fourth order Runge Kutta formula. That is, the fourth order Runge Kutta method is y1 is equal to y0 plus 1 by 2 into k1 plus 2 times k2 plus 2 times k3 plus k4, where k1 is equal to this one, k2 is equal to h in the f of x naught plus h by 2, y naught plus k1 by 2, k3 is equal to h in the f of x naught plus h by 2, y naught plus k2 by 2, k4 is equal to h in the f of x naught plus h, y naught plus k3. So these k1, k2, k3, k4 have a series form or a continuity. You can notice this continuity and by heart easily these equations. So now we will see an example, the particle in a box. For a particle in a box, we have to solve the Schrodinger equation to get the solution psi. That is d square psi by dx square equal to minus 2m by h cross square e minus v. So this is the into psi. This is the Schrodinger equation, time independent Schrodinger equation. So we have to solve this Schrodinger equation, that is, we have to integrate twice with respect to x to get this solution psi. So we set f2 of x, y, z, that is f2, a function of f2 as this one, this d square psi by dx square, which is equal to 2 minus 2m e minus v by h cross square into psi. So the solution will be the integral of d square psi by dx square, that is z is equal to d psi by dx. So integrating once more, that is by setting this z is equal to d psi by dx equal to f1 of x, y, z. Integrating, we get the solution psi, the wave function psi. The probability density then will be mod psi squared. The program is like this. We define the function f1 of x, y, z, that is d psi by dx, that is return d psi by dx equal to z, and f2 of x, y, z as, that is d square x by dx square. Initially it returns y, or here the y represents psi and this z represents d psi by dx. So we initialize this v, or the potential is 0, but inside the box the potential is 0. The mass is taken as 1, y0 is initialized as 0 and z0 as 1, and h bar is taken as 1. We input the quantum number n and the size of the box A. We calculate the energy E and the function, which was the constant part in the d square psi by dx square, that is 2m minus 2m e minus v by h cross square. Here this minus is taken here, so this is 2m v minus e by h cross square. Now the h, the increment h is taken as, or this dx is taken as 0.005. and the x0 is initialized as 0, and the empty lists are created for storing the results. Now a while loop is started. This K1, K2, K3, K4 is calculated for integrating this K, this Y, that is this K1, K2, K3, K4 are obtained for finding the K is equal to this one, and finally we calculate this y0 plus y0 plus k. That is the function, the psi is equal to y is obtained like this, y0 plus this one. So integrating in this step, this k, using k steps, we get the psi. That is, we integrate here, this h is dx, this f1 of x is d psi by dx. So dx into d psi by dx will give the psi. This integral will give psi, and this integral, that is this f2 of x, that is f2 is psi, and this function is the constant, that is d square psi by dx square. This is the d square psi by dx square into dx will give the d psi by dx. The integral of this L result in d psi by dx. Z is equal to d psi by dx. So these resulted values are appended here, and it is plotted. Plot x comma y as the displacement or the solution or the wave function, and the probability is obtained as this one, y0 into y, that is psi into psi, and this is plotted x comma yp, and this is legended using this line, and the outputted result will be like this. We entered here n as 3, size of the box as 5, and the wave function is like this blue one, as we expected, a sinusoidal one, and the probability density is like this one, a positive one. It is always positive. Okay, thank you for watching.